Hello, chemists. I want to talk about today's freezing lab a little bit because that lab really kind of introduces us to a lot of very important objectives from the course. And so it's kind of a good time to link those objectives directly to the lab in which they were introduced. So things that we learned today, or hopefully that you noticed, and I wish I did a post-lab video on every lab so that we could see exactly like what was it I was hoping you came away with, because we might all come away with slightly different knowledge. So here are some of like the primary things that I hope you noticed today. 1, melting and freezing point occur at the same temperature. The freezing point and the melting point of water is both 0 degrees Celsius. And sometimes that surprises people and sometimes they already knew that. Think of it like the freezing point is the doorway. That's the point at which something freezes or melts, and you can go in or out of the doorway. You're exiting the classroom and that might be freezing, or you're entering the classroom and that might be melting, but you do it at that same point. So those two temperatures are going to be the same, and that's not unique to water. That's going to be of any pure substance that you're looking at. Another thing I hope you noticed, the temperature does not change during a phase change. I think if we asked the average person on the street to graph what they think the lab quests would do when we looked at freezing point, we'd see some type of just very linear, it gets colder, and then somewhere along the way it freezes. But that's definitely not what we saw in the lab. And we don't do it for boiling, but we would see the same thing. There's actually a flat line that occurs during the actual phase change. So while water freezes, its temperature stays at 0 degrees Celsius, and it can't actually go below that in general, again, outside of those super cooling situations, until the freezing has finished. And that's cool. It's just cool because I think it's surprising. Again, I said that in lab. There's probably a lot more going on to freezing and melting than you think. Part of the reason that freezing, like particularly during freezing, that the temperature doesn't change is that freezing is itself an exothermic process. And this is a vocab word that you're going to see introduced a couple times. We're going to use it several times throughout the quarter. Exothermic means it releases heat. So when we're freezing something, it's getting colder, but the particles have to slow down. And since energy can't be created or destroyed, they have to give off that energy. In slowing down, they're losing energy, and that energy has to go somewhere. So it's released as heat. So we are essentially taking away heat. We're cooling it down as fast as it is releasing. And we get in a situation which we call a dynamic equilibrium, which is when you have two opposing rates occurring at the same speed. So we're taking away heat as fast as it's releasing heat, and so we see no net change to the temperature. And that's that flat line that you hopefully got to see in your freezing and your melting. And another thing that we saw today had to do with the freezing point of solutions and how they differ than the freezing point of the pure substance. So that's a vocab word and we're just throwing it out there. So let's take a moment to define it, because it's going to come up a lot in both chapter 5 and chapter 6, which we're covering here in unit 3. So solutions. A solution is a type of mixture. It's a particular kind of mixture, so this is obviously not a pure substance. If we were to view it at the Miss Frizzle level, we'd see different kinds of particles. Specifically, it's a homogeneous mixture. This is a very uniform mixture throughout the whole thing that's made of 2 or more substances that are evenly mixed. And because of that, we end up with kind of names or words for those other substances. We have the solute and the solvent. So let's go through solute first. So solute is the substance that is dissolved in the solvent. So you kind of have to have both of those words down, or the minor component of the solution. So it's the one that's present to the lesser degree. So a good example of that is this classroom here. This is a solution. It is made of air molecules, lots of different kinds of gas particles evenly mixed together. And some are, like the most common air molecule in this classroom is nitrogen, but some that are present in a much smaller, much more minor component are oxygen and carbon dioxide and argon to some degree. And so those are solutes. The nitrogen gas, the one that's the most common, then would be called the solvent. The solvent is the fluid, and fluid includes liquids and gases, the fluid in which the solute is dissolved, or the major component of the solution. So that would be the nitrogen gas. It's present in the largest extent. Or a lot of times, and this is, I'll have a little memory tip here with the V. There we go. Sorry, I didn't have my pen ready. The solvent is the fluid that does the dissolving. So a lot of times that's water. In fact, probably in the lab, I would say like 99% of the time, we're working with water as our solvent. It's the fluid that does the dissolving, that is dissolving the solute particles. So, we put salt into water in the lab, and so we made a salt water solution. You added ethanol in a tiny amount of ethanol to distilled water, so we made an aqueous ethanol solution. And so water was the one doing the dissolving. It was present in the major component. Salt water is kind of a good one for this as an example. If we have a salt water solution, the solution refers to the whole thing, and then the solutes would be those dissociated ions, because they are present in they're the substance that we've added and we've dissolved into the solvent. And then water is our solvent. It's going to be present in it's the major component, and it's the one doing the dissolving. And water is the solvent you're going to be experiencing the most in Chem 121. In my experience, students do not really struggle with these three words in terms of understanding what they are. It's mostly about getting them mixed up. So just to kind of review, a solution is talking about the whole thing. That the whole cup, the whole thing is the solution. The solute are the particles that we've dissolved into it, like our salt or our sugar or our whatever ionic compound we might have dissolved in. And our solvent is that major component fluid. It's the one doing the dissolving. So we looked at the freezing point of water as a pure substance. That's not a solution, just as pure water. But then we also looked at the freezing point of water again as a solution. We dissolved ethanol into our water. So in that case, our ethanol was a solute, and our water, commonly, was our solvent. And what we discovered is that the freezing point was not the same for water as a solution versus pure water. And what this phenomenon is called freezing point depression. So depression, not like it got sad, and doesn't want to go outside today, but as in it lowers. So the definition here, freezing point depression, the freezing point of a liquid goes down. It is reduced or depressed or lowered by dissolving other substances into it. So if you dissolve salt into water, the freezing point goes down. So instead of dissolving or freezing at 0 degrees Celsius, it might not freeze until -5 degrees Celsius. That means you can get the water colder than you could have otherwise. This is one of the reasons that we use salt to make ice cream. We don't put the salt in our ice cream because that would taste gross, unless it's like salted caramel, in which case it's amazing. But we put salt around the ice cream bin because it allows the water there to actually get colder than 0 degrees Celsius, and it makes the stuff in the milk crystallize better. Another way to say this exact same thing would be the freezing point of the solution is lower than that of the pure solvent. So the solution is the mixture. So when we mix stuff into water, its freezing point goes lower than pure water, so the pure solvent. And this is an example of a colligative property. So this is a cool word that you'll see on your blue page, and I referenced where it is in the book if you want to, for when, you're going to be assigned this reading, I believe, so, but just in case you want to double check on it, page 214. So a colligative property is a property that depends on the concentration of the solution. It depends on how concentrated it is. So the more salt you dissolve into it, that further changes its freezing point, as opposed to being dependent just on the identity of the particles. It depends on the concentration. And there's some other examples there as well. Vapor pressure depression, so the vapor pressure goes down when we dissolve something into a liquid. The boiling point gets elevated, boiling point elevation. So that's actually another reason we add salt to water when we want to boil it. It's because it actually elevates allows our water to go over 100 degrees Celsius, and it'll cook our noodles faster, because water will cook faster if it's up to 105 degrees Celsius instead of 100. And then also osmotic pressure. So be really paying attention to your blue page on what you're expected, because the book goes into quite a bit more detail here, and I want you to be really using your study time wisely. So it has quite a few equations that you're not expected to know, but you do want to know what a colligative property is, freezing point depression, and then those other examples. Now, I'm saying this word concentration, but we haven't really talked much in class about that. So concentration is a way to measure how concentrated something is. I probably, shared this, like my kids make really concentrated Crystal Light drinks, and I find them disgusting. But if I make the Crystal Light, they're really sad because they feel like they can't taste it. And we have a preference, a different preference regarding how many particles there are in a given amount of space in that drink. And there are lots of different ways to measure concentration, but the primary one that we're going to use in this class is called molarity. And it's abbreviated this giant, or its symbol is this giant capital M. And this M, this giant capital M, stands for moles per liter. So you can use either of those as its unit, the giant M, the capital M, or moles per liter. What you don't want to do is like capital M per liter, because that doesn't make any sense, because what you're really saying is moles per liter, which would be the same as moles. So you can use either of these when you want to express the units for molarity. And what molarity is it's the ratio between the total moles. And remember, moles are just a way to count particles. So we're talking essentially about how many particles are there per milliliter or per liter. It's really a density concept, except instead of comparing grams per milliliter, we're counting the particles. My kids like a lot of particles per milliliter of their drinks. I do not. So it's comparing the total number of particles counted through moles to the total volume. You guys know how I feel about this picture. Cracks me up. Not those kinds of moles, the Avogadro's kind of moles. And to calculate it, we would take the total number of moles of the solute, the particles that we've dissolved in, the Crystal Light, the table salt, the ethanol, and we would divide it by the total liters of the solution. Like how much do we have on a whole? And it's going to give us a comparison. So notice conceptually how similar this is to the concept of density, except in this case we're talking about those number of particles. And we see this line and we hear this per, and that should tell you anytime that we could use this as a conversion factor. And we can, and it can allow us then to go calculate and go between moles and liters. And this is going to be really important because we can make a really concentrated solution or a really dilute solution and then use that molarity to go between a measurable quantity and the atomic world. So let's practice. Let's look at what I'm talking about. What is the molarity or molar concentration? Those mean like the same thing. If 1.5 moles of sodium hydroxide is dissolved in water until a total volume of 100 milliliters is reached. So this problem is about molarity. What is molarity? And I'd encourage you for any of these practice problems on the video to go ahead and pause and try to solve it and then double check and pause. That's kind of one of the benefits. You can't pause me in the classroom. I mean, you can try, but it won't work. So what is the molarity? So we just discussed molarity is moles per liter. So if I'm calculating the molarity of this solution, I have 1.5 moles of sodium hydroxide, and I divide it by 100 milliliters. Now, moles is moles per liter, so either within my problem or before, I should probably convert to liters. Otherwise, I'm going to get moles per milliliter, and unless I remember to reflect that in my units, I'm going to probably end up reporting my molarity wrong. So I'm going to go ahead and convert before I do my problem. And I'm going to keep all these zeros, even though it's annoying, because I want to remember that all of those zeros were significant. So in the end, I don't want to forget and go down to like one significant figure. So when I do that, I get 15.0, and I'm going to use a capital M. And one thing to note, if I put this into my calculator is just going to say 15. It's going to give me a molarity of 15. But I'm smarter than my calculator, and I recognize that my weakest link here is this 3 significant figures. So I'm going to do that 0.0 so I don't get the sig fig stamp and lose points. So 15 moles per liter. Again, I could also do mole per liter as my unit. And that's how concentrated this is. This is a fairly concentrated sodium hydroxide solution. Now, let's talk realistically. How realistic is this of a problem for in the lab? Do I have a molimeter in the lab? No. No, in fact, measuring in moles is not actually practical because I don't have a device in the lab that can do that. Therefore, let's look at this problem, which is far more realistic. So take a moment to read that problem. If 5 grams of sodium hydroxide are dissolved in water until a total volume of 0.75 liters is achieved, what is the resulting solution's molarity? So this problem is asking the exact same thing as the last one. What's the molarity? And molarity is still moles per liter. The difference is it's actually a lot more realistic because I don't have a molimeter in the lab. I have a balance. And so it's given me the mass of sodium hydroxide. But do I know how to convert mass to moles? Do I know how to take a measurable quantity from a balance and convert that into how many particles it is? Of course I do. I just learned how to do that in the last unit. So in order to do that, I would have to figure out the molar mass of sodium hydroxide, which would take me to my periodic table. And I would need to consider that I would have 1 mole of sodium, which has a molar mass of about 22-ish, I think. Hopefully you have a periodic table closer. I have an oxygen atom, which has a molar mass of 16, and hydrogen. And when I add those all together, I get that the molar mass of sodium hydroxide is 40 grams per mole. So the molar mass allows me to calculate this. Because I've been given the liters, that's right here in the problem, I can just move that down right here, but I've not been given my number of moles. However, I have been given all the information to calculate it. And again, this is more realistic. Don't have a molimeter, but I have a balance. So let's convert 5 grams of sodium hydroxide to moles of sodium hydroxide. So the way to do that, I would do it through the concept of dimensional analysis. Maybe you have memorized to go from mass to moles. You need to do this with the molar mass, and whatever gets you the right answer is cool with me. But if I set this up, I see that I need grams on the bottom and moles on the top, because I always want the unit on the bottom to cancel out my measurement and the unit on the top to be the one that I'm headed towards. So then my 40 goes with that number, 40 grams per mole. And when I do that, my units cancel out. I'm left with the unit I want there on the top. I get 0.125 moles of sodium hydroxide. So when you go into the lab and you measure out 5 grams of solid sodium hydroxide, which you totally could do for me, you would have a little over 1/10 of a mole. And if you dissolved that into a total of 0.7 liters, so that the total was 0.75, you would get a particular molarity. So if you took that many particles, and remember moles are just a way to count particles, like the word dozen, divided by 0.75 liters, you'll notice these units don't cancel out, and they shouldn't, because our molarity is the molar ratio between moles and liters. And I'm going to have 2 sig figs. Remember, leading zeros are not significant. I end up with 0.17 moles per liter, or capital M. And you don't have to do both. I just like to specify that you can do either, but you can't mix them together. So this is a fairly low concentration of sodium hydroxide. Not a lot in that, but that's almost a whole liter. Think of your beakers, that a whole liter, and we're only dissolving 5 grams in there. Now this problem's a little bit different in the sense of it's asking you to describe how you would make the solution. So I pause the video and try to solve this problem yourself, and then listen to my explanation. So how would you go about making 50 milliliters of an aqueous solution of 3 molar sodium hydroxide with solid sodium hydroxide? So this problem is different in that it has given you a molarity. It's saying the end goal is that this solution would have this concentration. So how would we make it? Now you might be tempted to start your math here, to start with 3.0 m, but remember this has a per in it. This is a conversion factor. And we've talked about how you can't necessarily start with your conversion factor because that's like starting with the translator. And the translator in the story can't begin because they don't know what was said. So what we're actually going to do is we're going to take that 50 milliliters and we're going to answer the question, how many grams of sodium hydroxide do I need to add to that to make this molarity? So again, it's a really different kind of problem, and I hope you really tried it. So if I set this up, I start with the volume. 50 milliliters is going to be my final, that's the total that I want in the end. My first step here is going to be convert to liters. And I'm going to do that because I can't use this conversion factor unless I'm in the languages of it. And its language is moles per liter, so I do need to get into that language first. Once I'm in liters, then I can use it. And I can use it because I want to go, okay, for every one of these liters, I want it to contain 3 moles. So that's where I'm using it right here. I'm using it right in this step because it allows me to go from moles to liters like we looked at in the last problem, or liters to moles, which is our primary goal. Now I could stop there, but I don't have a molimeter in the this is moles of sodium hydroxide, by the way. I don't have a molimeter in the lab, so I'm actually going to go one more step to cancel out the moles and get into something measurable, which is grams. So I'm going to need that molar mass again. And the molar mass hasn't changed since our last problem. But if we didn't have it, or this was a new substance, we would need to use the periodic table to determine the molar mass of sodium hydroxide. So I'm going from a volume, and I want a particular concentration. Therefore, how much of that do I get? So before I do my calculation, I like to double check. Make sure my units cancel out, because that often shows me if I've accidentally set it up wrong. And I see that I'm at, okay, grams of sodium hydroxide. That's in general what I want. And I am limited. Here's my weakest link right here. My molarity is not an exact number. It's always going to have to be something I measured. I measured out this much. So I'm going to be limited by the error of my beaker and of my balance. So I only have 2 sig figs here, which in the end gets me to 6.0 grams of sodium hydroxide. So my real final answer, when it says how would you go about making 50 milliliters of an aqueous solution of 3 molar sodium hydroxide, what I would do is I would measure out 6 grams of sodium hydroxide in the lab, and then I would dissolve that in water and add water to it until I reached this total of 50 milliliters. And then I would know that solution had a molarity of 3 moles per liter. Now you can see I don't even have a whole liter. It's a concentration. So it tells me how much. So my final answer is add water to that until 50 milliliters is reached. And I have created a solution with a very particular molarity. So Whoops, it's hard to read that there at the bottom, but it says see Canvas Unit 3 module for extra molarity practice. We're going to be looking at molarity again next week when we do our titration lab. So you might want, and it's an objective on your blue sheet, so it's coming up on that Unit 3 exam. Let me know if you're having any trouble, and I can hopefully point you to some additional resources. And I'll see you guys soon.